It'd be nice if, we started class like this, like, it'd be more intimate setting.
Is this how like Cal 2 classes are?
No. This is what a graduate class looks like. It's like 8 people, 10 people at the most.
Really?
Most of the time. No, usually in the beginning. Well, it depends on what you're studying, I guess. When I was in school, my math, studying math, there was only 3 of us. So we would have to like petition to get a class to make. We were like, we need to graduate, like we need the class. There's only 3 of us. They'd run the class. Math, pure math. Yeah. So, all right, let's talk about the homework. Are there any particular ones you want me to go over on the max and min? Come on, this is your opportunity. How about 43?
Yeah, this is
F of t is t root 4 minus t squared. So should I start this thing? Yes. F of t is t root 4 minus t squared, and we're given the interval -1, 2. All right, so we're trying to find the maximum and minimum values of this function, right, on a closed interval. So let's make sure that our function is continuous, because we need that in order to use what we learned. So is it continuous?
Yes.
How do you know?
It's closed.
Is our function continuous here? So where's our function not defined, or where does it have trouble? Whenever this is negative, right? When that's negative. So it's continuous everywhere except where. So we need this to happen, right? In order for this to work, we need the radicand to be a positive number or possibly 0. We need to make sure that these numbers live in here. Now this right here is called a quadratic inequality. It's not a quadratic equation. So the way that you solve a quadratic inequality is different than the way you solve a quadratic equation. Let's see if we can do this. Anyone know how to solve that? There's like a set of steps that you do for it.
Can you set it equal to 0?
First, that's where you start. And you get 2 answers. 2 and -2. That's the solution to the equation, not the inequality. So what a lot of teachers do is teach that you draw a number line, and then you have to check these regions of the number line to see whether or not the t values in these regions work. Does this look familiar to you at all? Okay. So I would pick like -3 and see if it works. So plug -3 in right here. -3 squared is 9. 4 minus 9 is not bigger than 0. So this region would not work. And so I move to the next region. So I pick something in here like 0. And if I plug 0 in there, it does work. So everything there works. And then excuse me, I plug in like 3, and 3 will not work. So my region where this is actually okay is everything between here and here. So I'd say that t must be between -2 and 2. And t could actually be 2 or -2, because if it's 2 or -2, it's equal to 0, and that's okay to have this equal 0, right? So this is kind of like the domain, isn't it? This is the domain of the function. And we need to make sure that this is in there. Is that in there? Yes? Yes. So that is inside of here. So that means that we do have a continuous function on a closed interval, so we can continue. Now what you need is the derivative. And you need to take that derivative and set it equal to 0 and find out where it's undefined. So we need to look at the critical numbers. So how about we take the derivative? The derivative of this function, I will use the product rule, right? The derivative of t is 1 times the square root of 4 minus t squared plus, now you have to take the derivative of the square root of 4 minus t squared. So it's square root of something, derivative of that, 1 over 2 root t, or 2 root 4 minus t squared. Then times the derivative of what's inside, negative 2t. And then times t. Right? That's the t from the finishing the product rule. And in previous classes, we just tried to clean this up a little bit, and I encouraged you to try and match the back of the book, right? Right? Okay, and the reason I did that is because we now need to set this equal to 0. And so the cleaner this is, the easier it'll be to set equal to 0. Does everyone see I canceled out the 2's? I changed that minus right there. I changed it to a negative here. Or that negative changed that to a minus. T times t is t squared. All right, so if we're going to have to set this equal to 0 at some point, right, which we will have to do, I'm not going to do it yet, then I would always recommend if you have two terms like that, just put them together with a common denominator. So I have this. Imagine that that's over 1. So I'd have to multiply what here to get a common denominator? Root of 4 minus t squared on the top and bottom of the left one, right? So I'm going to introduce a root 4 minus t squared, root 4 minus t squared. See, I just don't understand it. Like, if the marker's dead, just like throw it away, right? Okay, here it comes. I can't see the basket. That one's better. So I'm introducing that on top and bottom. Now I still had the root 4 minus t squared over 1. And I'm not touching the other one, right? I'm just leaving this one. Now, something good happens there, doesn't it? On the top. These roots are basically going to come together. They go away. And so I should just get a 4 minus t squared on top. So we get equals 4 minus t squared. And then I can combine that with this numerator, so minus t squared. And then over the common denominator, which is now root 4 minus t squared, which is 4 minus 2t squared over square root of 4 minus t squared. That's my cleaned up derivative. So now what I'll do is I'll set it equal to 0, and then I'll figure out where it doesn't exist or where it's undefined. Any questions on the algebra? Yes?
No, it's all right.
Okay, I'll keep that here.
Take 2 out of the top.
Yeah, you could factor out 2. Mm-hmm. All right, so now it's kind of a separate thought. This is my derivative, right? First thing I'm going to do, I'm going to set the derivative equal to 0. So whenever I set the fraction equal to 0, we said you only have to worry about the top, right? So I'm actually just going to set 4 minus 2t squared equal to 0. And this really kind of depends on how you want to do this. I would probably move the 2t squared to the other side, to the right, and then I'd divide both sides by 2. And then I would take the square root, which would give me t is equal to what? Plus or minus root 2. So far, I have 2 critical numbers, unless they don't live in my interval. I have to check my interval, but I'll do that at the end, all right? So those are 2 critical numbers. I also need to, can I erase this now? Yes? Okay. I also need to figure out where the derivative does not exist. So that's the second thing I'm looking at. Where does the derivative not exist? And do we have an issue? Yes? No? Well, our derivative is a little different than the original function, isn't it? Because in the original function, could the square root part, could we get 0 under there in the original function?
Yes.
Yes. Can we get 0 under the root this time? No, because we'll have division by 0. Do you understand that? So actually, when t is equal to 2 or t is equal to -2, those are in my domain, aren't they? But they cause this to be division by 0. So these are actually critical points also. Question? Yes? Okay, so those are 2 more of our critical numbers. We think. We have to also look at our interval and make sure they both lie in there. Some of y'all are looking kind of crazy. Do y'all understand where these 2 come from? These 2 values are in our domain, but they cannot be plugged into the derivative because it'll make the derivative get division by 0. So they have to be counted as critical numbers. So once I find my critical numbers, I move on to the next step, which is to do what? After I found?
Plug them all in.
Plug them all into the original function, right? And plug in the endpoints, right? So I'm supposed to plug in all the critical numbers into my original function. F of root 2, f of negative root 2, f of, what, 2, f of negative 2. Those are my critical numbers. I'm also supposed to plug in the endpoints of the interval. What were the endpoints of the interval? -1 and 2. All right, so let's start eliminating some of these. Some of these don't even live in our interval. Which of these do not live in our interval? -2 doesn't live in our interval, and negative root 2 doesn't. Square root 2 is like 1.414, something like that. So negative 1.414 lives outside of our interval. Draw a number line, you can see it. -1, 2, that's where we're supposed to look. Negative root 2 is out here. Of course, -2 is even further out, so we can chunk those. So there's really only 4 points I have to check, right? Well, 3, because these are the same thing, aren't they? So I'm not going to check it twice, but I'm not eliminating it for the reason that I eliminated the others, just that I'm not going to double my work, right? So let's plug these in into the original function. The original function was t root 4 minus t squared, right? So in this case, it would be root 2, that's t, times square root of 4 minus, what's this squared? 2. I'll do it, root 2, but then squared. So this is root 2 times root 2, which is 2. That's if you're adding, right? It would be. So this is root 2 times root 2, that's the same as root 4, which is just 2. So when you plug in root 2, you get 2. Let's see what happens when I plug in -1. -1, right? It's t, which is -1, square root of 4 minus, what's t squared? Just +1. So this becomes negative root 3. And then finally, plug in 2. You get 2 root 4 minus, what's 2 squared? 4, 4 minus 4 is 0, so you get 0. Any questions? Okay, so what's my absolute maximum? What's my absolute minimum? -2 and, well, yeah, sorry, 2 and negative root 3. So how did I say I prefer that you write it? The absolute maximum, I said write it as an ordered pair, like a point. So the x-coordinate followed by the y-coordinate. It would be the root 2 followed by the 2. And then the absolute minimum would be -1, negative root 3. All right? Now I'm going to graph this function in a second. But what I want to do is I want to put a problem up here for you to start working on while I'm setting up my computer to graph. All right? I would like for you to practice one. Did anyone try number 49 yet? Did I give you just the odds or everything? Just the odds? Anyone get to 49 yet? No? Okay, why don't you, let's try 49 then. Why don't you see if you can work 49 out? I'll put the problem up here for you. It was f of x is natural log of x squared plus x plus 1 on the interval -1, 1. And I did not do that in class, right? Okay. So the question, of course, or what you're being asked to do here is find the absolute maximum and absolute minimum values of this function on this interval. That's what you're supposed to do. All right? Have at it. I'm going to set up my computer here. How are y'all doing with the derivative on that one? Does it work out okay?
We're still working on a domain.
Still working on domain. If you're working on the domain, All you need is to guarantee me that this right here is always bigger than 0. It's not? When is it equal to 0? Well, if you try the quadratic formula on this, right? Then, right, so what you need is this, x squared plus x plus 1 to be greater than 0, strictly greater. So you try and figure out where it's equal to 0. And when you try quadratic formula, when you get to the part on the quadratic formula that's square root of b squared minus 4ac?
Yeah.
Okay, when you get to that, boy, I just had like this major, forgot. Okay, it's what? B squared is 1 minus 4 times a times c. This is what? Negative number, right? You can't take the square root of a negative number. So, well, you can't in this class. So here we go. It's never equal to 0, which means that this parabola is either always above the x-axis or always below the x-axis. My guess is it's above. So take any number you want. Doesn't matter what it is. Plug it in here. Is it positive or negative? Positive, no matter what. Pick any number. So that's what that's saying. If it's never 0, if this is never 0, then it's got to always be positive or always negative. Understand?
Mm-hmm.
So it's always positive, which means the domain is everything, all real numbers.
About 0, right?
0 works. Yep, right, because natural log of 1 is 0. Yeah. While you're working that out, I'm going to do the work up here myself. Then I'll talk through it when I'm done. Is that enough time?
Yeah.
Yes? I'll walk through this one with you. Oh, well, you know what? Before I walk through that, that's the problem that we did before. The t square root of 4 minus t squared. And we had tested 3 points. We tested -1, we tested square root of 2, and we tested 2. And we said the max happened at square root of 2, which is right there. Maximum value of, what was it? I thought it was 2, wasn't it?
Oh, we're looking at the side.
Oh, it was -1 and 1.
Where was the minimum on the previous problem?
Oh, -1, -2.
negative 1, negative root 3. This does not look right.
This is the first point you have on the left.
Look at, do you see what's wrong, why I'm having a problem? My x-axis doesn't look right.
I noticed that last class too.
There's something wrong with the actual program itself. It didn't graph that properly. It's saying, look, it's saying that this point right here is about 1.4 out and almost 2 high, but look at the 2 here. That doesn't make any sense. Something's wrong with the actual program. I probably have to close it and bring it back up, which I'm not going to do. Okay, let's get to this. All right, so your function is this. We talked just briefly that the domain of this is all real numbers because it's impossible to make this negative. It's always positive. So your domain is everything. You take your derivative. Derivative natural log of something is 1 over it times derivative of what's inside. Slide this up top. And then we say, OK, when is this derivative 0? Only when the top is 0. Solve, you get negative 1/2. All right, when does this derivative not exist? Well, that's when the denominator, right, is 0. But we already said that had no real solutions. So we don't have to worry about this. There's really only one critical number, right? Negative 1/2. So what I do is I take that critical number, I plug it into the original function. I take the 2 endpoints, plug them into the original function. Make sure that the critical number lives in this interval, which it does. So when you plug them in, you got to be careful. Plugging in negative 1/2 in here. Do all your little work, and you should get natural log of 3/4. Then if you plug in negative 1, you should get natural log of 1, which is 0. And if you plug in 1, you should get natural log of 3. So which of those is the biggest number? What's the biggest one? Natural log 3 is your max. So this is going to be your max. It's going to come from the point 1 natural log of 3. And your minimum? Natural log of 3/4. This is actually a negative number. This is a negative number. So you might be looking and say, oh, 0 is going to be my smallest. No. Natural log of 3/4, if you do it on your calculator, it's negative. You go back and look at the graph of natural log. That's the graph of natural log, right? At 1 at 0, but to the left of 1, like at 3/4, it would be below the x-axis, so it would be a negative number. So this would be your min. And that would be the point, negative 1/2, natural log of 3/4. All right, this one I'll try. I'll reopen that program and see if just closing it down helped it figure out who the hell it was or who it is. Let me see. So it was natural log x squared plus x plus 1. I'm graphing that. There's the graph. And if I restrict that graph just to, where was it? Negative 1 to 1, then it's just that piece. And we said that we're going to have a maximum at 1 natural log 3. Do you all agree? Looks like the computer figured out who it was, right? 1 root 3, yeah, at the end point. And then the minimum is going to happen at negative 1/2. Looks good to me. Yeah? Okay. The algebra in these problems, each problem presents its own unique algebra problem, all right? So please make sure you do go through these. I would encourage you to work through the odds like I told you, right? Odds. But then I would encourage you to go back and do the evens, at least the evens for 37 through 50. Do you want to do one more? Or
Yes.
one more? Let's do... let's do number 50. I mean, usually the further back in the set they are, the harder they are. Not always the case, but let's see what happens with this one. I think I'll do this one a little backwards. I think we'll graph it first, and then we'll come back and answer the question. So f of x is x minus 2 arctangent of x, and we're on the interval 0 to 4. Let's take a look at that. X minus 2 arctan of x on the interval 0, 4. That's the graph. Okay. Wonder what it would look like if I didn't restrict it, if I just went negative 10 to 10. There's the graph of the function, not restricted on that interval. But if I restrict it on that interval, this is a good opportunity to talk about this. Does that function, okay, I'll draw it here also. Does this function have an absolute maximum? No, not like this. If the domain's not restricted, it has no absolute maximum. Has no absolute minimum, does it? No. But it does have a local maximum, right? And a local minimum, if I look at the whole picture. Local max, local min. What we're doing is we're saying, all right, if we cut this picture off between 0 and 4, and just look here, then it definitely does have an absolute maximum and it definitely does have an absolute minimum. We should be able to find them. Next time, not after we get through the next section, the section after that, what we do is we open it up where we're not restricting it anymore. We try and find those 2 points, all right? So back to this 0, 4, and there it is. So I'm thinking that our minimum should happen where? At x is 1, and it looks like our maximum should be happening at the endpoint 4. Okay. All right. Derivative? Or do you want to talk domain? You want to talk domain first? Okay, what's the domain of this? Well, x, you can plug anything into x, right? That's arctangent. So there's a couple of ways you can do this. I would recommend that you go back and remember what arctangent looked like. I mean, tangent looks like this, right? That's what the tangent function looked like. So what does arctangent look like? This is tan x. Do you remember this? Didn't you learn in college algebra or something like that that all inverse functions are reflections over the identity? So like this, the inverse of tangent should look like this, something like that. And it does. It goes like that. That's what arctangent looks like. So tangent has a restricted domain, and the range is everything, right? But the inverse tangent is the opposite. It has the domain is everything, but its range is restricted. They're inverse functions, right? So that's why they're like that. So this was arctan. So do we have any domain issues with this at all? No, no domain issues. So our domain is all real numbers. Okay, keep that in mind as we move ahead. Now let's take our derivative. Derivative, it's a pretty clean derivative. Derivative of x is 1 minus 2 times now derivative of arctangent. 1 over 1 plus x squared. So this is equal to 1 minus 2 over 1 plus x squared. And what have we been doing every time we've had something like this? We've been combining these together and to get one fraction, right? So let me get a common denominator. I have to put 1 plus x squared on the top and bottom here. So I'm going to have 1 plus x squared. Then I'll have the minus 2. And then over 1 plus x squared, right? I'm trusting everyone here could get to that. Yes. Which is the same as x squared minus 1 over 1 plus x squared. That's a pretty cleaned up version of my derivative. Set it to 0, right? I need to figure out where it's 0. That's going to be when x squared minus 1 is 0. And we're all calculus students, so plus or minus 1. Either by difference of squares or by moving the 1 over square root, plus or minus, right? What about where the derivative does not exist? What's going to screw up my derivative? Only if I get division by 0, right? Can I get division by 0? No, because it's 1 plus x squared. No matter what you plug in for x, you square, it's going to be positive, or 0. It could be 0, right? But you add 1 to it, there's no way that's going to be ever going to be 0. Right? Do y'all, yeah? Yeah? Okay. So no issues here? So I have two critical numbers. So what I'm supposed to do now is I'm supposed to plug these critical numbers into my function. I'm supposed to plug the endpoints into my function and compare them. One of these doesn't belong, right? The negative 1 is not in my interval. I'm only looking between 0 and 4. But didn't that pick up that other side? Remember that other hump on the other side? That's where the negative 1 came in. But we're not looking over there. Right? That original picture was like that. That negative 1 is this one, but we're not looking at that part. Do you see the danger in that? You could accidentally use that one and think it's part of your graph, but you've already cut that piece off. So you're not allowed to look on that region. All right, let's plug in 1. Uh-oh, we have to do arctangent of numbers? Uh-oh. Okay, f of 1 is 1 minus 2 times, what's arctangent of 1? It's the angle that you get when you take tangent of that angle, you get 1. What is it? Thought I heard it. Pi over 4. It's where you get root 2 over 2, root 2 over 2. See, this is root 2 over 2, root 2 over 2. If I ask you what's tangent of this angle right here, you would do that divided by that, right? Which would be 1. This is saying the opposite. It's saying at some angle, I'm taking tangent, I'm getting 1. Where is it happening? It's happening at pi over 4. So this is going to be 1 minus 2 times pi over 4, which is just 1 minus pi over 2. One minus pi over 2. All right, I'll figure out that might be my highest point. Oh, no. It's going to be my lowest. Okay. All right, next one. 0. That's always fun to plug in. 0 minus 2 times arctangent of 0. At what angle is tangent 0? Zero. Again, go here. Where is my y-coordinate divided by my x-coordinate? 0. Right here, 1, 0. If I take my y and divide it by x, I get 0. Doesn't it happen back here also? Why am I not looking back here? Domain restriction on arctan. Arctan is restricted to the 0 to pi over 2 and then negative pi over 2. So my answer here would be 0 times 2, 0, so that whole thing's 0. What about 4? Yeah, 4 minus 2 arctangent of 4. That is not a common angle, is it? That's not one of the ones you should know. Like this one, everyone should be able to recover where this happens and where this happens. That one, not so much. So I heard triangle. I still think you'll need, at some point, a calculator. Right? What does it look like it is? Well, it's not a nice number, right? At 4, it looks like we're at like 1 point something. So at this point, I would just get the calculator out. Make sure you're in, well, it won't matter for this, but yeah, make sure you're in radian mode, because it's going to spit back an angle to you. And you don't want that angle in degrees, you want it in radians. You get 4.34? No, 1.34. So I'm going to continue that up here. It's 4 minus 2 times 1.34. And when you do all that, what do you get?
Oh, I'm sorry. The whole answer.
Oh, the whole answer.
Yeah.
Okay, you already did it all. All right. What was arctangent of 4? Someone could get that, just the arctangent of 4.
1.32.
1.32. And then when you do that, you got 1.34 roughly? Okay. So where do we have a maximum? Well, the things we're getting out are 0, 1 minus pi over 2, and 1.34. So this is the max, right? So you get a max. It's happening at 4, 1.34. And you have a minimum, which is happening, well, this one right here, 1 minus pi over 2, which turns out to be whatever that is, decimal-wise. I'm going to leave it as an exact number. I'm just going to leave it as 1 minus pi over 2, which would be acceptable on a test, to just leave it as that. All right? We good? All right, work through those. You know, I know that some, like I said, the algebra in some of those is unique. But we're going to proceed to the next section now. Do you remember this? Before I do this section, do you remember the problem that I gave you where you had a building and a river? Does this look familiar? Wasn't that on the review for, right, one of the first exam? There was a building and we were trying to find the cost function. Okay, I know some of you worked this and some of you didn't, but we're going to do this problem pretty soon. You basically have two buildings, A and B, and you're trying to connect them with fiber optic cable or something, and you decide that, oh, and this is a river. So you decide that you're going to run your cable along the river, along the bank, you know, underground, and then at some point you'll cut across. And the cost of burying the cable underground is different than the cost of running it under the water. It's more expensive to put the cable underwater than it is to go underground. And so what we try and do is we try and find a cost function, all right? And I know we did it, right? We came up with a cost function. So we came up with a cost function, and it was something, okay? It was a function. And then we actually, that function was a function of x, where x is the distance from here to here. And I don't recall how long the river, or how far down the river was, but I'll say it's 200 feet or something. If you look at this, if I can come up with a cost function, and this is my picture, can you tell me my restriction on x from that picture? The x that I choose has to be between where and where? 0 and 2. So I have 200, right? So what I have is a function on a closed interval that I'm trying to find the minimum of, because I don't want to pay that much. I want to pay the minimum cost. So the way you do it is exactly what we just did. So that's where we're headed. You're going to have a word problem that we translate into a function. You're going to try and find the highest or lowest point. You'll need to know if you're on a closed interval or not. If you are, you'll do what we just did. If this is not a closed interval, we have a different method. Does that kind of make sense? I know we went through that, so does that kind of, all right. Don't worry, we'll get back to it. We'll have time to practice. All right, but we're going to take a little detour, and we're going to talk about the mean value theorem. So we know that the value of a function, right? The value of the function is the output, right? Right? When we say, hey, what's the value of that function at 2? It's the output when you plug in 2. So when we say mean value theorem, is that a value that comes out of the function that's all pissed off? Is that what it means? Is that the mean we're talking about? Like all upset? Like, I did not want to go through that function? What does the mean mean? What does the mean mean for us here? Average, right? That's another word we use for average. So this is a theorem, very important theorem, about the average value of a function. And I did a video on it, but I'll go through it. Let's say you have a function that is continuous, connecting 2 points together, right? What happens in between really does not matter too much, all right? Doesn't matter at all. As long as it's continuous, I can draw without picking up my pencil. The average value, okay, of this function, the average is going to be equal to the slope of the secant line. I'll try and convince you of that in a second, all right? If I take this line connecting the two, right? I'm saying the slope of that line is the average value of the function. So a bunch of different things came out of this function, right? A bunch of different y values. If we take all those y values and we take their average, it should be the slope of that line.
Isn't that like the trend line? Isn't that a graph?
Yeah, pretty much, yeah. So here's another way of explaining it that I think will make a little more sense. If this is time and this is distance, right? Then the slope of this line, rise over run, would be your ending distance minus your ending time, right? Ending distance minus starting distance. Yeah? So the slope of that line would be the ending distance minus starting distance over what? The run would be from here to here, which would be your end time minus your start time. But it's distance over time, right? So this is speed. This gives us the average speed, doesn't it? I said distance. Please, let me go back through that again so I don't confuse you. If you take a graph of a curve that this curve is connected by a continuous function, the slope of this line isn't the average height, okay? It's the average change of this over this. So like speed, right, was distance over time. Distance divided by time. That average for your trip here is the slope of that line. That's not news to us. We already kind of knew that from when we first started this. What the mean value theorem says is that your average value, your average speed, you're guaranteed that somewhere inside of here you actually attained that same average speed. So if I look inside this interval, let's say that this is A and this is B, then we're saying that somewhere inside here, not at A and not at B, somewhere in here, I actually have the same slope as the secant line somewhere on my graph. The tangent line is parallel. So I don't know, maybe about right here. Do you agree that if I draw the slope of the tangent line there, that those two are parallel? Yeah? The mean value theorem guarantees that that has to happen. All right? It has to. In fact, in this particular problem, it probably happens in two different spots. Would you agree? But you're guaranteed it happens at least in one spot. Yeah? Now, it all kind of stems from what's called Rolle's theorem, which is the theorem that goes before this one. Rolle's theorem is a little easier to visualize. If I have a function that starts here and ends here, I have to connect, so same line. If I connect them with the nice smooth curve, then do you agree that somewhere in here, the slope of my tangent line is 0? So somewhere in here, slope of my tangent line is 0, which is parallel to the line connecting the two, right? Now, if you take this theorem, Rolle's theorem, and you just turn it sideways, you actually have the mean value theorem. It's just a rotation of this. Make sense? So what we are interested in doing in this section is I'm going to give you a function on a closed interval that's going to be continuous. But instead of asking you, to find the absolute maximum and absolute minimum like we just were doing, I'm going to say, since it's continuous on a closed interval, it satisfies the mean value theorem, the conditions. So tell me where in there these two lines are parallel, or where this line is parallel to that secant line. You have to find out where it's happening. All right? Do you understand geometrically what we're trying to do? Yes? All right. So how about the theorem? You want the theorem? You want to write it out? We'll write it out real quick. The theorem is much uglier when you look at it than to see it visually first. Let me see. Mean value theorem. Suppose, have I used that? Suppose, all right. That word, that stands for suppose. I'm not making that up, okay. They actually use that in mathematics to short. We like to abbreviate everything in mathematics to make everything look like a bunch of symbols that people don't understand, right? That's what we do. We just make a bunch of symbols so people don't know what we're doing. So suppose f is a continuous function on the interval, the closed interval AB. And we have another condition. And f prime exists on the interior of AB. So we have to be able to take the derivative inside this closed interval. That's an important condition. You'll see, I'll give you an example in a second of where if that condition's not met, this theorem falls apart. So you have a continuous function on a closed interval. The derivative exists inside there. Then, here's what we have. Here's a conclusion. There exists at least one point, which I will call x equals c, in the interval, in the interval AB, such that the following is true. So I'm about to write what is going to be true, but remind you again, we have a continuous function on a closed interval AB, right? And I can take the derivative everywhere in here, and the derivative exists. That means I don't have any what's in here. For the derivative to exist, I don't have any jumps would make it discontinuous though, right? So I already know I don't have jumps. What types of things can't I have in here?
Points or holes.
There you go. Corners, cusps, things like that. Vertical, tangent lines. the derivative has to exist in here. So I don't have anything crazy like an absolute value function or something. If that's true, then there has to be some point in here, somewhere, C, there's got to be at least one, that when I plug that in and I take the derivative, the slope of that tangent line is equal to the slope of the line connecting those two, right? That's what I need to say. So here's how we say that. There exists a point, C, somewhere in there, such that the derivative at C is equal to f of b minus f of a over b minus a. Do you agree that the slope of this red line right here is f prime of c?
Yes.
Do you agree that the slope of this line right here is f of b minus f of a, that's rise, right? The distance from here to here, that's rise. That's f of b minus f of a over run. Run is from here to here, that's b minus a.
So that the slope is equal?
That's the slope of the secant line. So that's what this is saying. This is the slope of the tangent at C is equal to the slope of the secant on AB. So connecting the two ends. You see it? All right. That's the mean value theorem. There's another way to visualize or to think about the mean value theorem. When you drive your car from here to wherever, let's say you drive for 3 hours, you go 150 miles. What was your average speed? If you drive for 3 hours, you go 150 miles. What was your average speed? 50 miles per hour, right? Was your average? That was your average speed? Yes? That's the slope of the secant line. What the mean value theorem says is that somewhere in your trip, you had to have gone 50 miles per hour. That it would be impossible to average 50 miles per hour without at some point looking down at your speedometer and seeing 50 miles per hour. It might happen more than once, might happen a bunch, 10 times, 20 times, but it has to happen at least once. It's impossible for you to have an average speed that you never attain. Got it? That's more of a real world type driving thing. All right, so let's see how we can do this. And then I'll share with you one of my favorite problems. Okay, 2 o'clock. Oh, why do we have to be differentiable? Let me show you that before I do this example. What if I have this? A function that does that. Is that continuous? Continuous, yes, right? Is it differentiable everywhere on the inside? No, it's got a problem right there, right? We can't take the derivative. So this means that the mean value theorem is not guaranteed to hold. And it's not going to, because what's the slope of the secant line? It's that red one, right? Is there anywhere on the curve where your tangent line is parallel to that? Never, right? If you're anywhere along here, what's the slope of your tangent line? This. If you're anywhere here, it's this. They're never going to be parallel. That's why you must have that condition that the derivative exists on the inside. Seems subtle, like, okay, why is it there? Do you really need it? Yes, you absolutely have to have it. It guarantees us, the derivative existing guarantees us a nice curvature to our function, that we can't just all of a sudden change speeds. It'd be like driving, you're going 60 miles an hour, you're driving, and all of a sudden, boom, you're at 30 miles an hour without a nice shift of moving down from 60 to 30. If you could do that, right, flip, then it would be